Imagine every ocean, sea, and deep basin on Earth suddenly containing fresh water instead of salt. At first glance, it sounds like a gift: drinkable seas, easier desalination, less corrosion. But the planet's chemistry, biology, and climate are tuned to salinity. A wholesale shift to fresh water would cascade through marine life, global circulation, weather, human industry, and food systems in ways that are rapid, complex, and often catastrophic. Let's begin with the living world, a realm intricately woven into the very chemistry of the ocean. Every marine organism, from the smallest bacterium to the largest whale, is exquisitely adapted to the specific ionic balance of seawater. For countless millennia, life has evolved within this stable saline environment. Most fish, crustaceans, mollusks, and plankton have developed sophisticated biological systems for osmoregulation, actively managing their internal salt concentrations to perfectly match the surrounding sea. But what happens when this fundamental constant is suddenly removed? An abrupt drop in salinity triggers a catastrophic cascade, starting at the cellular level. The immediate effect is severe osmotic shock. Without the external saline pressure they are built for, water floods their cells in an uncontrollable rush. For many, this means their cells swell and burst, leading to rapid death. For others, critical metabolic pathways simply shut down, unable to function in the diluted internal environment. The devastation would be starkly visible in ecosystems like coral reefs. These vibrant cities of the sea are built by tiny calcifying animals that depend entirely on the stable chemistry of seawater to construct their calcium carbonate skeletons. Lower salinity dramatically disrupts carbonate saturation states, making it impossible for them to build their homes and accelerating the dissolution and decline of existing reefs. At the base of the food web, phytoplankton communities would be completely upended. The ocean's primary producers, countless species of salt-tolerant diatoms and coccolithophores, would perish. In their place, freshwater-tolerant phytoplankton groups like cyanobacteria would attempt to take over, fundamentally altering the ocean's primary productivity. The immediate biological result is a mass mortality event of staggering proportions, concentrated among specialist marine taxa. This triggers a severe simplification of global food webs and a desperate scramble for newly vacant ecological niches by the few euryhaline and freshwater-tolerant species that can survive. A conservative estimate is that a vast fraction of existing marine biodiversity would collapse within months to years, with extinctions heavily concentrated among thermohaline species, those with no ability to tolerate changes in salinity. The symphony of the ocean would fall silent. To understand the full impact, we must consider the fundamental physics of the ocean. The engine of global ocean movement is driven by two key properties: temperature and salinity. Together, they control seawater density, which in turn powers the vast thermohaline circulation. This is the planet's great conveyor belt, a slow but powerful system connecting the sunlit surface waters with the immense dark deep ocean. The name itself, thermohaline, comes from the Greek for heat and salt, highlighting their critical roles. The principle is simple. Salt increases water density, making it heavier, while fresh water is lighter. If our oceans were to become significantly fresher, this delicate balance would be upended. The less dense surface water would struggle to sink, even in the frigid polar regions where deep water formation is normally initiated. Consequently, the great overturning circulation that transports enormous amounts of heat poleward would weaken, stall, or dramatically reorganize. Regions that currently enjoy temperate climates, sustained by this oceanic heat transport, northwestern Europe being the canonical example, would face profoundly altered weather patterns, potentially cooling significantly despite local sea surface changes. Furthermore, reduced deep mixing severely limits the ventilation of oxygen to the deep ocean. So paradoxically, even though freshwater can hold slightly different dissolved oxygen concentrations, the primary effect of a circulation slowdown would be a catastrophic increase in deep ocean hypoxia, as life-giving oxygen could no longer be replenished from the surface as effectively. The ocean's chemical cycles would fundamentally change too. For millennia, the composition of seawater has remained remarkably stable, providing a consistent medium for life. The salts dissolved within it are the primary actors in a vast chemical theater. Chloride, sodium, magnesium, calcium, and sulfate ions are the key players in acid-base buffering, carbonate chemistry, and precipitation reactions that regulate the entire planet. Removing this salinity on a global scale would shatter that equilibrium. The carefully balanced carbonate system, which dictates the ocean's pH, would be thrown into disarray, with profound consequences for the ability of organisms to calcify. The very building blocks for shells and skeletons, carbonate ions, would become scarcer. This threatens not just familiar creatures like corals and clams, but the microscopic plankton that form the base of the marine food web. Consequently, some of the planet's most vital processes for sequestering carbon would break down. The biological pump, driven by sinking plankton, and the carbonate pump, from shell formation, would falter. While it's true that fresh water generally dissolves CO2 more readily than saline water at the same temperature, this is a dangerously simplistic view. The catastrophic loss of marine biological carbon export would almost certainly overwhelm any minor gains in CO2 dissolution, drastically reducing long-term carbon sequestration in the deep oceans. The net climate impacts are complex, depending on countless timescales and feedbacks, but there is no simple, more CO2 uptake outcome to offset the certainty of a global ecological collapse. Surface processes and weather would shift. Sea salt aerosols, tiny droplets lofted from breaking waves, are major sources of cloud condensation nuclei over marine air masses. These particles influence cloud reflectivity, lifetime and precipitation patterns. A salt-free ocean would sharply reduce sea spray aerosol production, modifying cloud microphysics and likely reducing some types of low marine cloud cover that cool coastal regions. That, combined with reorganized ocean heat transport, could change rainfall patterns regionally. Monsoon systems, coastal precipitation and storm tracks could all shift, with consequences for agriculture and freshwater availability on land. Freezing and ice dynamics are affected as well. Salinity depresses the freezing point of seawater. Typical seawater freezes around 1.8 degrees C, not 0 degrees C. Freshwater freezes at 0 degrees C, so polar seas would start freezing at higher temperatures. In a colder region that edges climate thresholds, freshwater oceans could lead to increased seasonal sea ice formation in some areas, altering albedo and local ecosystems. Yet, because circulation changes redistribute heat differently, the net effect on polar ice cover is complex and region-dependent. Human systems face immediate shocks. Fisheries collapse is the clearest and fastest socio-economic impact. Most global fisheries target marine species that would decline or vanish in a freshwater ocean. Coastal communities, industrial fishing fleets, aquaculture operations, and the markets that depend on seafood for protein would face sudden shortages. The livelihoods of hundreds of millions of people would be disrupted, and global food security would take a major hit unless rapid terrestrial or controlled environment substitutes are scaled up, which is costly and slow. Shipping and naval architecture would require rethinking. Saline water is denser. Ships float slightly higher in seawater than in freshwater. In a global freshwater ocean, ships would sit deeper, increasing draft and possibly limiting access to shallow ports and canals designed for current buoyancy. Ballast operations, hull fouling communities, and corrosion behavior would change. Some corrosion modes driven by salt would decline, others driven by biological colonizers or different chemistry could increase. Offshore platforms and moorings would experience altered load distributions. The global shipping economy would need port upgrades, dredging changes, and vessel modifications at large scale. There are public health angles. A fresh ocean might appear to offer a vast reservoir of potable water, but logistics and pathogen risks make direct use impractical. Surface freshwater bodies can still harbor pathogens and require treatment. Moreover, the hydrological cycle depends on salinity gradients. Evaporation, transport, and precipitation patterns shift when ocean temperatures and chemistry change. Sea salt aerosols and marine-derived minerals contribute to nutrient deposition on land. Removing those inputs could affect coastal soils and even remote terrestrial ecosystems that rely on marine aerosols for micronutrients. Coastal protection and sediment dynamics would shift. Salinity influences the buoyancy and flocculation behavior of suspended sediments and colloids. Freshwater favors different flocculation and transport regimes, altering turbidity and sediment deposition patterns in estuaries and deltas. Mangroves and salt marshes, ecosystems dependent on saline tolerance, would collapse and likely be replaced by freshwater wetlands or terrestrial vegetation, with major biodiversity and carbon storage consequences. What about the timescale of the change? A gradual freshening over centuries might allow some evolutionary and ecological adaptation. Estuarine and euryhaline species might expand, and new stable communities could emerge in shallow coastal zones. An abrupt switch, imagining some conceptual mechanism that stripped salts quickly, would produce an extinction pulse, oxygen and nutrient anomalies, and cascading failures across fisheries and coastal economies. Recovery to a new quasi-stable state might take centuries to millennia, and the resulting ecosystems and human arrangements might be dramatically different. Agriculture and resource systems would respond unevenly. Some coastal aquaculture that currently struggles with salinity intrusion might thrive, while open ocean aquaculture of saltwater species would collapse. Freshwater ocean surfaces would change weather and nutrient deposition for coastal crops. The global pattern of food production would thus require reconfiguration. Investments in freshwater aquaculture, land-based protein alternatives, and massive research into breeding salt-tolerant crops would only partially replace lost marine protein. Finally, there are feedbacks to climate and long-term habitability. Changes in ocean circulation and aerosol production feed back onto atmospheric temperatures and precipitation. The loss of efficient deep ocean carbon storage reduces the ocean's role as a climate buffer. The combination of ecological collapse, shifting climate patterns, and infrastructural stress would make adaptation costly and geopolitically fraught. In summary, an ocean turned freshwater is not a benign improvement. It undermines the physical and chemical scaffolding on which marine life and global climate depend. Expect rapid biodiversity loss in marine specialists, fisheries collapse, reconfigured ocean circulation and weather, altered ice regimes, and deep socio-economic consequences for food, transport, and coastal communities. Some localized benefits, reduced salt corrosion in certain contexts or temporary increases in CO2 solubility, would be overshadowed by systemic disruptions. The planet's coupled systems evolved with salinity as a central parameter. Removing it fundamentally changes Earth's operating point. Subscribe to the channel for more what-if facts.